So what I want to talk about right now is atomic orbitals, and this is stuff, again, that you should already know from your previous chemistry coursework. But if you are considering a carbon atom, or any atom in general, the sorts of orbitals that are involved in making of bonds with other structures include the 1s inner core of electrons. So if you're a hydrogen atom, you actually use the 1s orbital when making bonds. But if you're anything more complicated than that, you tend not to use the 1s. It just has a pair of electrons in it. Then you have the 2s orbital, which is similar to the 1s in shape in that it is round. But unlike the 1s, it has two different lobes with electron density. There's actually a node in between the inner shell and the outer one. But for the purposes of seeing what the geometry of it looks like and thinking about how it interacts with other things, this is the way it's usually drawn as a solid sphere. So the two p orbitals involve three different directions. There's specifically a y direction, which would be up and down most of the time, and then we have an x direction, which would be in the plane of this board, and then we have the z direction, which is sort of in and out. And the p orbitals then are 90 degrees to each other, but they are also involved in standard bonding. So if you think about the actual energies involved with a carbon atom, the 1s orbital is very low in energy relative to everything else. And there are two electrons that hang out in that 1s orbital, and we never think about them for bonding purposes. They are not part of the valence shell. Meanwhile, in the valence shell, in the 2 shell, you have a 2s orbital, which has a pair of electrons in it, and you have 2p orbitals. Again, there are 3 of those, and you have 4 total electrons to mix among these. And traditionally, the way you would draw that is something like this. Now, you would put 2 of the electrons paired in the 2s orbital, and then you'd have 1 each in 2p orbitals, and then 1 p orbital would be empty. So that's the way the structure looks when it's just sitting by itself. If you have a carbon atom just sitting by itself, not interacting with any other molecule, then that's the electronic picture. That's where the electrons are. Those are the orbitals that they're in. And then sort of the way the orbitals look is basically sphere, larger sphere, and then these sort of dumbbell shapes that have directionality to them. Again, up, sideways, or in and out. But if you are going to try to make a bond to a new object, or in this case, if you're going to take a carbon atom and make methane from it, then you're going to make a CH4, and you're going to have to spread out 4 things as best you can in 3-dimensional space. And 90-degree angles aren't going to cut it in 3-dimensional space. So in 3-dimensional space, we know that methane has to look like this as the final answer. We know that it has to have 4 bonds that are identical to each other. And, moreover, we know that the bond angles involved here are going to be 109.5. They can't be 90 degrees. So we can't use the standard p orbitals to make those bonds. And there's certainly nothing in there, the s orbital, which is relatively small and relatively relatively tight to the carbon atom. So we can't be using these orbitals as drawn. We have to do something else. Instead, what we do is we hybridize all of those orbitals. And so rather than having 3 individual 2p's and a 2s, what we end up making is 4 separate sp3 type orbitals. And again, there's going to be 4 of those. And so then you're going to end up using these 4 electrons from the carbon, and you're going to put 1 in each. And then in order to make the actual bonds, then you're going to take 1 electron each from each of the hydrogens, and then that gives rise to the actual structure involved. So the key thing that we understand is that these orbitals, as drawn, cannot possibly make this bonding picture. Therefore, these atomic orbitals have to be hybridized into 4 different sp3 orbitals in order to orient in the right direction. And I'm going to illustrate that now. Okay, so here we're going to illustrate hybridization for the simplest case, which is to say a carbon atom that's trying to make a bond in both directions to the hydrogen and also a single bond to the other carbon. And so it needs to make a single bond in both directions simultaneously, but this is specifically the x direction because it's the plane of the board. So the orbitals that are going to be mixed together in order to accomplish this are the 2s orbital, which is almost always mixed in because it's the lowest energy orbital, as well as the 2px orbital because we need the x direction. And so the way this works is that whenever you combine 2 orbitals, make a linear combination of orbitals like we're doing here, you need to mix together the 2s and the 2px in the same phase direction and then the opposite. So the easiest way of thinking about that is to then change the phase of the orbital. And arbitrarily, I've decided to change the phase of the 2s orbital. So basically, the idea is that here we're mixing together the 2s and the 2px orbital, and here we're using the opposite phase of the 2s and also the 2px orbital. And the reason why you do that is relatively complicated, and it's sort of mathy explanation behind it. But the core idea is essentially that whenever you mix together two orbitals to begin with, you need to generate two orbitals. And you're going to do so by summing the phases as drawn, and then flipping the phase of one of them, and then summing that as is. And the way this generally works mentally is you have to think of summing together a wave function. So this is basically constructive interference. So anywhere where you have the same phase, it mixes together. Anywhere where you have the opposite phase, it cancels. And so what this means is this top orbital ends up having a very elongated positive phase and a very small, relatively, negative phase. And again, this is a relatively arbitrary distinction. So this node right here is still going to exist, but it actually shifts over relative to what it was. Where this was positive, ends up growing. Where this was negative relative to that positive, it ends up shrinking. And that's going to be one of the two sp orbitals that you generate. Of course, the other 2sp orbital is going to be exactly the opposite. The positive phase is going to be in that direction, and then the negative phase is going to be in the other direction. And that's what you end up generating. So you mix together two orbitals, and you have a relatively symmetrical sphere plus a directional p orbital, and what that ends up doing is creating a much more directional 2sp type orbital, and here it would be in the x direction. And let's arbitrarily say that that's in the positive x direction, and then this would be 2sp in sort of the negative x direction. But the point is, again, when you mix together the s and the p's, you end up forming much more directional orbitals, and so then you end up with something like that. This is how a carbon atom can make two bonds. Rather than using an s orbital, which is relatively low in energy, and a p orbital, which is relatively higher, what it does is mix those two together, create two sp type orbitals that are the same energy, one that points more to the left, one that points more to the right. So now let's imagine that we're going to extend the idea further. We've created the two sp orbitals that point in left and right directions, but now we're going to mix in another p orbital, and this is because now we need to make three bonds, one that's going to be vertical, and then these two as well. And this is now going to be an sp2 hybrid because we have to mix in two orbitals. We have to mix in the x direction because that's the plane of the board, and now we're going to have to mix in the y direction as well so as to form a bond that's largely up there. I'm going to spare you the exact details of how this works, but again, what we have to do is mix in the py orbital now, and that's going to be largely so it ends up pointing vertically, and we have to create a linear combination of orbitals. So we're going to take the two sps that we already have, two of those, add one more, so we need to end up with three orbitals. And the upshot is that the three orbitals you're going to end up with largely look like this. One that's almost entirely vertical. That's because you're largely using the py orbital and relatively little of the px components because it's basically straight up and down. But then that also is going to create two orbitals now that point essentially in the sideways directions with a very little bit of sort of the negative component here. So you end up having what essentially amounts to three separate sp2 orbitals, one that points almost entirely vertically, and then these that point down here. And that's how this carbon atom makes the sigma bonding framework with the hydrogens and the oxygen. So of course, for the final extension of the idea, what we need to do now is simply mix in the z component. And so that involves using the orbital that comes mostly toward me and toward you, the one that looks basically like that, and that would be the pz orbital. And that's because right now everything is in the plane, but if you want to spread things as far apart as you can in 3 dimensions, then you have to push it toward the camera, and then toward me. So what you basically end up doing is taking the 3 sp2 orbitals that we've already created, they're right there, and now mix in a pz component. And again, the details are not really the point, but you end up making 4 sp3 type orbitals, all that have the same energy, and that's the best way to spread things out in three-dimensional space. So the last thing to think about here is that when you are using an sp3 hybridized set of atomic orbitals, when you have used every single one of the p orbitals, then obviously there are no p orbitals left over. You have created 4 new orbitals because you mixed together the 2s and the 3 2p's, and that has led now to this best case scenario of being able to spread something out 109.5 degrees from each other. However, if you fail to mix in the z direction because you're building something that's in the plane with the px and the py, an sp2 hybrid, then there's a leftover p orbital. And that p orbital is basically sitting right here, coming toward me and going back out toward you. And that is the leftover pz orbital, which has not been used. So if you have an sp2 orbital, set of orbitals, 3 orbitals in the plane, then what's left over not being used for sigma bonding is the pz, which again is towards the camera and towards me. Likewise, and same idea, if you have an sp set of hybrids, then you've only generated 2 orbitals, and you've essentially used the s orbital, and arbitrarily I chose the px direction, which means left and right, which means that unused right now and still available for bonding of other variety is going to be the py direction, which is to say up and down, as well as the pz direction, which is to say toward me and toward you. So when you are mixing together atomic orbitals to create hybridization, what you are doing is trying to orient things as best you can in three-dimensional space. If you need to make 4 bonds, the best you can do is 109.5, and the way you achieve that is by making a linear combination of all 4 of these orbitals. However, if you're trying to spread it out as much as you can in 2-dimensional space, trigonal planar, then you're going to use the x and the y and the s, and you're not going to use the pz, which means that the pz is left over for double bonding. Likewise, if you only need to make 1 dimension, then you can use, say, the px orbital, and that means that the other 2 orbitals are left over for pi bonding. So the py is left over up and down, and the pz is left over here as well. So this is atomic orbitals in a nutshell.